Hey class, welcome to week 3. We're going to be talking about discrete probability and stream ciphers. This is going to be a longer slide, so please make sure to take some breaks throughout this. I'm going to try to illustrate it as the best as I can. So if there's any questions, feel free to just send me emails or um, just send some questions over my way. So the first thing we're going to do is we're going to give a high level overview of discrete probabilities. We won't go into much of the mathematics of it, but we're just going to be talking about general terms, and then you'll see how they actually apply to cryptography. So discrete probability concerns events with distinct and separate outcomes. It is a cornerstone of cryptography as well as allows us to analyze the likelihood of different outcomes, enhancing our understanding of cryptography systems and security. Perfect. So for probability basics, before we dive into the meat of the topic, let's establish some of the fundamentals. An outcome is a result of a single trial of a probability experiment. An event is one or more outcome of an experiment. The sample space is the set of all possible outcomes, and probability is a measurement quantifying the likelihood that an event will occur. Perfect. So some basic probability rules. So two key rules govern probabilities. The sum rule says that if sorry, the sum rule says if events are mutually exclusive, the probability of either occurring is the sum of their probabilities. The product rule states that the probability of two independent events occurring together is the product of their probability. So some examples that we have here is rolling the dice and a coin toss. So we're going to talk about some key terms that are going to be helpful when we discuss about probabilities. Conditional probability is the probability that an event is given that an sorry. A conditional probability is the probability of an event given that another event has occurred. So the calculations that we have here is using that formula. So we have probability A and B equals the likelihood of B divided by the probability of B. For example, if we are drawing cards from a deck, the probability of drawing a queen given a face card is the face card would be. Let me do this again. So for an example, if we are drawing cards from a deck, the probability of drawing a queen given a card is a face card would be considered the conditional probability. Now, when we talk about random variables, so random variables are variables whose outcome results from a random phenomenon. For example, the sum of two dice rolls is a random variability, as it can take on any value from 2 to 12, each with a certain probability. We're going to talk about probability mass functions or PMF. So the probability mass function gives us the probabilities for distinct random variables. For an example, the PMF of a single die roll would give each outcome from 1 to 6 a probability of 1/6, since there's 1/6 probability that you could get any number. The expectations or expected value is essentially the average outcome of a random variable. If you were to perform the experiment a very large number of times, for a dice roll, the expected value would be 3.5, calculated as the sum of the outcomes from 1 to 6, each multiplied by their respective probabilities, which is 1 divided by 6. So now we're going to actually talk about how does discrete probability play into cryptography. So we're going to talk about discrete probabilities in cryptography in the actual space that key space analysis. So let's consider an oversimplified encryption schema where the key is a single digit from 0 to 9. In this case, our key space is 10. If an attacker tries to guess the key, there's a 1 in 10 or 10% chance that they will succeed on any single guess. This simplified scenario shows us how the size of the key space influences the probability of an attacker's successful guessing the key. In practical sense, secure cryptographic systems, we aim for a unanimous key space to make the blunt force attacks infeasible. So there will be so many different outcomes that they would not even have a good or high probability chance of attacking. Next, we're going to talk about cryptanalysis. So let's imagine that we have a encryption algorithm that, when encrypting a large set of plain text, outcomes an unusual high number of ciphertexts starting with the same letter. This is not what we would expect if the encryption algorithm was secure. The outcomes should appear random and show no distinguishable patterns. By calculating the distinct probability of this event, we could show that this um, deviation from the expected uniformed distribution is a statistically significant, indicating a potentially a weak algorithm. Next, we're going to be talking about the cryptography of random number generators, or the RNGS. Now imagine a simple RNGS designed to understand a dice roll by generating a number from 1 to 6. The distinct probability of any particular number appearing should be 1 to 6, or 1 divided by 6, as we mentioned. If we roll this virtual die many times and notice that the same number comes up far more frequently than they should, this would suggest that the RNG isn't as random as it needs to be. In cryptography, in most cryptographic systems, high quality randomness is crucial for tasks like generating secure keys. Next, we're going to be talking about hash functions, which is another fundamental of cryptography. Now, let's suppose that we have a simplified hash function that assigns a number from 1 to 1000 to each to every word in a document. Using discrete probability, we can calculate that if a hash two different words, sorry, that if we calculate that if we hash two different words, the chance of them resulting in the same hash value would be 1 in 1000. In real cryptographic hash functions, we aim to minimize the probability of collisions, which is actually the collisions are the hash values. So we aim to minimize the probability of collisions because they can lead to security vulnerability. Next, we're going to be talking about errors detected and corrections. Now, let's imagine that we are sending data packets consisting of sequence of 3 bits. To detect errors, we add a particular bit at the end of each packet, which is set to ensure that the total number of 1 bits in the package is always even. If a single bit occurs, if a single bit error occurs during a transmission, the receiver will notice an odd number of 1 bits rather than the even uh, the even bit that we indicated earlier, indicating an error. This basic form of error detection demonstrates how distinct probabilities can help ensure data integrity during the transmission. Okay, perfect. I know we just talked about a lot of different things, so if you want to take some time and just take a moment and think about what we just said, I have some practice quiz questions that we are going to review that will better help assist through all the with these terms that we went through. So for this first practice quiz, we're going to do some matching. So take a moment and jot down what terms match what definitions. Okay, perfect. Now to give you the answers, and I think I can make some adjustments on here. So give me 1 second. Let me get out the pen. Okay, Perfect. So we understand that. So when we look at key terminologies, right? So what is a key space analysis, right? Is it this first one here? Is it the discrete probability helps to design error detection and correcting code to ensure data integrity? Not really. Um, since that sounds like another one here, and that actually sounds like our error detection and correction. So move that over here. That's a one-to-one match. Perfect. Let's actually start with definitions. Distinct probability helps us understand the quality, understands and quantify just how random, keyword random, and secure these outputs are. So that actually sounds like our random number generator. Okay, perfect. Now, next one is discrete probability is used in analyzing, keyword analyzing, the probabilities of cryptographic hash functions such as the likelihood of a collision. When did we talk about a collision? When two different inputs produce the same number. What does that sound like to you? That is actually hash functions. Okay, so far we've got three terms out, three terms in. Next, so cryptographers use discrete probability to guess the calculation. Sorry, cryptographers use discrete probability to calculate the likelihood of a successful guessing and a key in a blunt force attack. So for this one, this is considered the key space analysis. Okay, and then the last one, this is actually going to be discrete probability can help analyze the security of cryptographic algorithms. If a cryptographic algorithm produces an outcome, like a ciphertext or a hash output, that does not appear random and show patterns, it could potentially be broken or attacked. So, what is this definition lying towards? And the last one we have here is this one here. Okay, perfect. Let me erase all that. Next, let's go on to the next one. Oop. Okay, so that's one that we have here. I'm going to stop the video here, cut it off here, and then for the next video, we're going to talk about stream ciphers.